Hello, good morning everyone. In the last lecture, we started discussing about flip-flops. So a flip-flop is a electronic circuit which has got two stable states, that is the 1 or 0. So these are the two stable states and that can be used to store a binary data informations. In flip-flop, the stored data can be changed by applying various inputs. This flip-flop or latches, which are the fundamental units of the digital electronic system, such as computers and other communication systems. And in this class, last class, we discussed about RS flip-flop, which is also called the set reset type of flip-flop, which can be used for setting and resetting applications. But we found that in that particular truth table, we found that when this set and R inputs are high, that is S is equal to 1 and R is equal to 1, which leads to a forbidden state. That's why the output state, both the outputs we are getting at the higher level, which is not allowed according to the basic definition of a flip-flop. When one output is high, the other output supposed to be low. So that is violating the fundamental flip-flop principle. So that is a forbidden state. So in order to avoid that, in this lecture we consider the clocked RS flip-flop first. That is for for changing the output. For a normal RS flip-flop, the output keeps on changing according to the input signal, which is not favorable in most of the cases. So in order to control that, we use a clock signals which will enable the output change only when there is a triggering clock pulses. So after that, we discuss about JK flip-flop, which can avoid the the forbidden conditions. That is, when both inputs are high, the output keeps toggling. So that we'll discuss that. After that, this JK flip-flop is also having some limitations. So then we'll discuss about the master-slave type of JK flip-flop, which is more kind of more perfect kind of flip-flop systems. So in this class we will discuss about all these things. So we have discussed this part, that is in an RS flip-flop, which is basically a 1-bit memory bistable device, which has got two inputs. One will set the device, that is the output will be 1, and other we can reset the device. So this was the block diagram, which all this part we discussed in the last class. That is, the S are the inputs and Q bar are the outputs. So this RS flip-flop can be constructed using NAND gates and NOR gates. So this is the simplest one, that is using NOR gate, where this is cross-coupled one. So the input of one of the NOR gate is coupled into the output of the other one. Similarly, for the output of the first one is coupled to the input of the second one. So these are the output, R and S are the output inputs, and Q bar are the output. So when the inputs are zeros, when both inputs are zero, we'll get the same state. So whatever was the state before, it can be 0 1 or 1 0, it will remain the same after inputting these two values, x is equal to 0 and r is equal to 0. That is no change conditions. In the next case, when we input 0 to S and R to 1, that is the reset conditions, where the output Q will be 0, that is the correspond to the reset conditions, and when S is equal to 1 and R is equal to 0, then Q will be 1. So that corresponds to the set conditions. And when both inputs are 1, the output will be undefined, cannot define what will be the state of the systems. So that is called the forbidden state. Now, in the digital circuit, the output of any circuit should not only depend on the input circuit. So in the last slide, we discussed about the RS flip-flop, where the output will be entirely depending on whatever data given into the input. But in addition to that, there should be a kind of triggering mechanism so that we can have a synchronized operation of the the system. So in the normal RS flip flop or RS latch, as soon as there is an inputs R and S available, that output will be changing according to that. So in order to have a control on the state, we need to have a triggering systems. For that, we use a triggering clock signals. So this kind of flip flops are called the clocked flip flop. So this is a clocked RS flip flop. So this is the block diagram or symbol for the clocked SR or RS flip flop. And this previously there was only SR, inputs are SR and Q bar, but there is a clock enable into this particular systems. So in order to construct a clocked RS flip-flop, we consider the those RS flip-flop using NOR gates. Previously, we directly connect the S and R into these two terminal, but in this case, we use additionally two AND gates, and one of the input of the AND gate is connected to clock signals. So both of these inputs are connected to the clock signals. So according to the according to the Boolean expression or whatever the logic diagram of the AND gate, the output will be active only when both inputs are high. So in this case, when clock signal is 0, so let's say that the clock, there is no clock, we are giving 0 clock pulse, there is no clock pulse here. So that means input to both these AND gates are 0. So that means these two AND gates will not be active. That means these data are not transferred. So whatever we give it to the S or R terminal, that is not transferred to the this NOR gate, so that the Q and Q bar remains same. So that is a no change condition. So there is, if there is a no clock pulse, whatever the inputs here, so whatever this input here, so the S and R, it corresponds to the no change. So this is not only for S is equal to 0, R is equal to 0, this is applicable for all values of all combinations of S and R. So it's supposed to give cross in these two columns. So when we give a clock pulse here, so that means this will be active. So these two AND gates will be active. So in that case, it will act like a normal SR gate, SR flip-flop. So that means when clock is active, if we give 0 0 into the inputs, that means the 0 0 will be passed on to these two terminal. So that means the output will be remains the same. So that is just like the previous normal SR flip-flop, where if you are inputting both S and R is equal to 0, corresponds to the no change state, no change state. So this truth table is not complete. I will in your lecture note I will include the correct one. So you're supposed to have one more column here, and when the clock pulse is high, so this all these arrows corresponds to clock activated signals. So when clock is activated, 0 0 no change, when 0 1, that corresponds to the reset. R is equal to 1 corresponds to reset, where Q is equal to 0, the output is 0. When S is equal to 1 and R is equal to 0, which corresponds to the set state, where output is 1. So that is correspond to the set conditions. Again, when clock is activated and both S and R is equal to 1, which leads to the forbidden condition. So that is not allowed. So when the clock is high, the input AND gates act as the input follower. So that means only when clock is active, this AND gates will act as a input follower, so that you'll get it works like the normal SR latch. But when the clock is deactivated, the output remains the same. So these two AND gates are not connected. I hope you are clear with this. This is the corresponding clocked latch RS flip-flop using NAND gate. So in this case, instead of the AND gates and NOR gates, we use all instead of using AND gates and NOR gates, we use all NAND gates. So we replace these two AND gates with NAND gates and all these two NOR gates with NAND gates, so that again this will be active when the clock pulse is high. So whenever the clock pulse is high, when we are giving 1 to the clock pulse, you will get output will be changing according to the inputs. Otherwise the output will be when the clock is low, that means output remains no change conditions. So that is corresponds to the no change conditions. So when clock is high and S is equal to 0, R is equal to 0, again corresponds to the no change. When clock is high, S is equal to 0 and R is equal to 1, corresponds to reset, where Q is equal to 0, Q bar is equal to 1. And when clock is high, S is equal to 1, R is equal to 0, corresponds to the set conditions, where output is high. And when all these three are higher, that is correspond to the invalid conditions, just like the previous RS flip-flop. The both inputs are higher is not allowed. Remember, when we use NAND gate for RS flip-flop, the inputs we consider are S bar and R bar, because this is not gated here. So when we discuss about the drawbacks of the RS flip-flop, it can be both normal or clocked RS flip-flop. There is an invalid state. When both inputs are higher, the output is we cannot define the output, so that is an invalid forbidden state, and the flip-flop is operated in the invalid state for a long time, which can damage the flip-flop itself. So this is not favorable for a flip-flop for a memory device. Then we need to consider different type of flip-flop. The JK flip-flop is most widely used of all flip-flop design and is considered to be a universal flip-flop circuit. Both S and R inputs of the previous SR bistable flip-flop are now replaced by two inputs, which are called the J and K respectively, which are under the name of the inventor, the Jack Kilby. The J.K. corresponds to the Jack Kilby, the name of the inventor. So here the J is corresponds to S. So J is equal to S and K corresponds to R. If you look into the internal architecture of this JK flip-flop, so just like the clock RS flip-flop, there is a clock signal here, but the two input AND gates of the gate SR bistable are now being replaced by the two inputs NAND gate of the previously discussed the gated SR bistable flip-flop are now being replaced by three input NAND gates. So previously these two were two input NAND gates, but now it is three input NAND gates, where the third input of each gate is connected to the output. Here you can see that that corresponds to the J input. The third input is connected to Q bar, the Q bar output, and the for the second one that corresponds to the K input NAND gate, the third input is given to the Q. So this cross coupling is given, so there is a feedback. So that makes our circuit so this cross coupling of the flip flop allow the previously invalid conditions. So previously there was an invalid conditions where both S and R is equal to 1, which is now becomes toggle action. So whenever there is this when both inputs are high, there will be toggling of output. So that means if previously it was 1 0, now it becomes 0 1. So the output will change. So then the JK flip-flop, we can see that the JK flip-flop is basically an SR flip-flop a clocked SR flip-flop but with a feedback, and this feedback which enables only one of its two input terminals, either set or reset, to be active at any one time, thereby eliminating the invalid conditions seen previously in the normal SR flip-flop circuit. But there is also another problem with this kind of JK flip-flop. That is, whenever suppose the clock signal is keeps higher, it is at the positive end. Then, if both inputs are higher, so when J is equal to 1 and K is equal to 1, and clock is also higher for a long period, the output Q will toggle as will keeps on toggling. So it will keeps toggling 0 1 1 0 like that, which makes the output of the flip-flop unstable or uncertain. So this problem is called the race around condition in JK flip-flop, and this problem can be avoided by ensuring that the clock input is logic 1. The clock will be at the higher state only for a short period of time, but that is very difficult. So if you want to reduce that, the frequency of the clock pulse according to the our design, that makes the circuit more complicated, and it is not easily achievable. So this in order to avoid these conditions, so the race around conditions, we introduce another concept called the master slave JK flip-flop. The master slave flip-flop is basically a two-gated SR flip-flop connected together in series configuration, with slave having an inverted clock pulse. The output from Q and Q bar from the slave flip-flop are fed back to the input of the master. So this is the master JK flip-flop and this is the slave flip-flop. So output Q is connected feedback to the K input of the master. Similarly, the Q bar is connected to the J input of the master. So this feedback configuration from the slave output to the master input gives the characteristics toggle effect of the JK flip-flop, which we'll discuss later. So so basically this is RS flip-flop with feedback, and also there is a two JK flip-flop which are connected in series, and the clock pulse to the first one is this one, which is inverted and given to the slave. So there is an inverter here. So that makes when the clock pulse is high, this flip-flop will be active and this will be inactive. So that means when the clock is high, when we are giving input here, correspondingly you will get Q and Q bar here. But as soon as the clock pulse goes to the negative triggered, when it is going to the downward, so that means this will be active. So this is a inverted one. So when it is going to the negative pulse, when there is a negative triggered pulse, this clock will be active and this will be inactive. That means whatever was the output here, that remains there, and which will be fed into the slave. So the output now will be according to whatever states before. So the slave will follow master. So that's the name. The slave is always follow what is the output of master when there is a negative triggered pulse. So when the clock is high, the master is operational, and when the clock is low, the slave is operational. The output changes once in a clock signal, clock cycle. The working of the master slave flip-flop. So when the clock pulse goes to 1, so when it is going to the higher state, the slave is isolated. We see the previous slide, when this is clock is high, the clock to slave will be 0. So that means this is inactive. So that is isolated. When the clock goes to 0, so similarly when the clock is going to 0, the information is passed from the master. So whatever information is the output of the master, which will be passed to the slave, and output is obtained accordingly. So now we'll consider different conditions for the truth table conditions. For example, if j is equal to 0 and k is equal to 1, so that corresponds to reset conditions. So j is equal to 0, k is equal to 1 corresponds to the reset conditions. So then the q bar will be high. So reset condition means the q bar. So q bar of the master will be higher. Of the will be higher, which goes to the k input of the slave, and the clock forces the slave to reset. So when j is equal to 0 and k is equal to 1, so qr will be higher, which is passed on to the slave. So this is higher and this is 0, so this will be reset condition. So that generate a reset conditions. And if j is equal to 1 and k is equal to 0, the q will be higher. So when j is equal to 1 and k is equal to 0 mean q, so that corresponds to the set condition, the q will be higher. So that will pass to j and k during the next negative pulse. This will be passed on to j and k respectively, 1 here and 0 here. So that corresponds to the set condition. So q will be higher. In that case, the q will be higher. If j is equal to 1 and k is equal to 1, so that was the critical one. When both inputs are higher, it toggles on the positive transition of the clock, and thus the slave toggles on the negative transition of the clock. So that slave output will be toggled only during the negative transition of the clock. And similarly, when if both j and k is equal to 0, that will when both this j and k will be 0, that means that this will be inactive and the output remains the same. So that is the no change conditions. So here only difference will be when both inputs are higher, when j and k is equal to 1. So we'll consider these corresponding conditions when both j and k is equal to 1. This is the corresponding timing diagram. When the clock pulse is going to the positive signal, so when this suppose that initially the output is 0, the q output is 0 and q bar is equal to 1. So when clock pulse is going to higher state in the positive pulse, so that will make the q of the master. So initially it was 0, so it will toggle. So the toggling is the conditions. So when so during the positive half cycle, we consider that the q and q bar, q is equal to 0 and q bar is equal to 1. So when we give the positive triggering pulse here, this will toggle. So that means q become higher. So initially it was 0, now it becomes higher. It goes to the higher state, and that happens. And during the negative pulse, it remains the same. The output will be here. There is nothing will happens, but when we are giving the negative pulse, the output remains the same here, but this will be active. So this slave will be active, and that makes the slave to the q output of the slave to the higher state. It goes to the higher state, and only when the next positive pulse clock signal arrives, the q will be toggled. The q of the master will be toggled to the lower state, but it does not change the output of the slave, which remains the same, which that will be remains the same. Only when there is a negative pulse, this will this will be affected. So this will be transferred to this one. Whatever the state of master will be transferred to the slave at the negative pulse, so that goes to lower state. And during the next positive cycle, the q of master goes to high, and this remains the same. And only when the negative pulse, when there is a negative pulse, it copies what is having the master. So the slave actually follow master. So this pulse will be the pulse width remains the same, but it follows the master. So this is like this. So there is a lag. So this master slave flip flop, which will lead to the unwanted toggling inside the JK flip flop. So it will toggle the negative the firstly the this flip flop, as the clock the As the clock input of the slave flip-flop is inverse of the master clock input, the slave flip-flop does not toggle immediately when master is toggling. So the output from the master flip-flop are only seen by the gated slave flip-flop when the clock input goes low to the logic 0. So it will happen only once in a clock signal. The toggling will happen only once in a clock pulse signal. With that, we will conclude this lecture, and the next class we will discuss about the T and D flip-flops.